Assalamu alaikum. Welcome back to Sir K Loves Physics and Chemistry tutorial. Today's episode is an enrichment lesson on DC circuits involving resistances in series parallel combination, including Wheatstone bridge. So join me till the end of this video. Watch and learn. Shown in figure 1 is a direct circuit with four resistors connected to a battery with an EMF of 6 volts. The two 3 ohm resistors are connected in series, and the 4 ohms is connected in series also to the 2 ohm resistor. So we have our first question, letter A. What is the potential of point A relative to point C in this figure? We also have question letter B. What is the potential of point B relative to point C? All right, in the figure. And question letter C. What is the potential of point D relative to point C in this figure? Question letter D. What current flows from the battery in this circuit? And the last question for number 1, what is the potential drop from point A to point B in this circuit diagram? So, our answers in question letter A to question letter E, all right, we say that the potential of point A relative to point C must be 6 volts, all right? And for question letter B, the potential of point B relative to point C must be positive 3 volts. All right. So, why do we have these answers? As shown in the diagram, the potential difference across points AC, all right, we can figure out that across points AC, right, the EMF or electromotive force of the battery, which is 6 volts, all right, is exactly the potential difference, all right, across points AC, all right, and that is positive 6 volts. Now, the potential of point B relative to point C is positive 3 volts because we know that the current is the same for resistors in series, all right? And since the two 3 ohm resistors are equal, each of them must get half of the total voltage. All right, that is positive 6 volts divided by 2. All right, so that is why the voltage of BC, all right, must be positive 3 volts. Now, for question number 1C, okay, the potential of point D relative to point C must be positive 4 volts. And for question letter D, the current that flows from the battery, all right, is considered the total current generated in the circuit, and that is equal to 2 amperes. And the last question, letter E, the potential drop from point A to point B must be equal to positive 3 volts. All right? So, why are the answers to question C, D, E? We will find out in just a short while because we are going to explain and calculate, all right, for these quantities that we have just mentioned. We start our computation by getting the total resistance in the circuit, all right? We label that as capital R sub T, all right? So using a derived formula, whenever we are getting the sum of two resistors that are connected in parallel, all right? The formula is uh, the product of the two resistor or resistances divided by their sum, all right, will be equal to the value of their combination. So that is what we use here as our basis. So again, you will notice that the two 3 ohm resistances, all right, are in series. So their total must be 6 ohms. And that goes through also for the 2 ohm and the 4 ohm resistances. Their sum is also 6. All right. And if you're getting the combination of the two 6 ohm resistors or resistances connected in parallel, all right, so we simply multiply their product is 6 ohms and 6 ohms, all right, to be divided by their sum, which is of course 6 ohm plus 6 ohms. So 36 ohms squared divided by 12 ohms, that will give us 3 ohms as the total resistance of this circuit. All right. So that will now allow us to find the total current or the current that is flowing from the battery. Okay. The current that is generated by the battery having an EMF of 6 volts. If we divide the EMF by the total resistance, then we are getting the total current labeled here as I sub T. All right? So that is 6 volts divided by 3 ohms. Of course, that is 2 amperes. All right? So that is the total current or the current that flows from the battery. Now, uh, you will notice that there is a junction, which is point A here. All right? Another junction is point C. So, imagine that the current, total current, 2 amperes, all right, goes from the positive terminal of the battery, all right, as soon as it uh, passes through the junction point A, this current of 2 amperes will split, all right, into two subcurrents. That is, we label the current passing through uh, the path ABC as current IB or I sub B, while the current that goes through the path ADC is labeled here as I sub D. So each of these two currents, IB and I sub D, must be equal to half, all right? Half of the total current, that is 2 amperes divided by 2, all right? Of course, that is 1 ampere. So in the diagram, we label these currents, okay, and their directions with these arrows, right? Now, the potential at point B relative to point C, that is, all right, the voltage B sub BC, all right, is just determined by applying Ohm's law. That is, the current passing through this resistance is 1 ampere. That is current I sub B. So multiply that by the given resistance of 3 ohms. We, of course, get, okay, the potential at point B relative to point C, which is positive 3 volts. The meaning of the positive is just emphasizing that point B is at a higher potential compared to point C. All right? And likewise, the potential um, at point D relative to point C is also the product of the current I sub D, which happens to be also equal to 1 ampere. So if you multiply that by the given resistance of 4 ohms, we also get as the value of B sub DC equal to positive 4 volts. Again, we say it is positive because the potential at point D must be higher compared to point C. All right? We are getting their difference, and that difference is equal to positive 4 volts. And finally, the potential drop, all right, from point A to point B, labeled here as B sub AB, is also the product of the current I sub B multiplied by the given resistance of 3 ohms. And that is, of course, equal to positive 3 volts. So this is what we call the potential drop, okay, from point A to point B. We call it potential drop because uh, we just mentioned a while ago that the potential at point A must be higher than the potential at point B. So we are literally saying that the potential has dropped, all right, from point A to point B. And that is the same as the potential difference, all right, across points A and B. And that is equal to positive 3 volts. Shown in this next direct current circuit, all right, is an example of what we call Wheatstone bridge, also known as the resistance bridge. It is used to calculate the unknown resistance, labeled here as resistance X, okay, by balancing two legs of the bridge circuit. One leg includes the component of unknown resistance, which we said is labeled here as X. All right. And the resistances labeled M and N are actually known resistances. All right. And resistance P is a variable or adjustable resistor. All right. So, um, a galvanometer, right, which is a device that can measure small amount of current, all right, it is uh, connected between points B and C, and it is controlled by a switch S2, and there is an EMF source such as a battery, all right, connected, all right, at points A and D, all right, and uh, the current that is generated, okay, by the battery, of course, is controlled here by a switch, all right, S1. The current that flows through the galvanometer, of course, depends on its potential difference across points B and C. All right, so to emphasize, resistances M and P are resistances that can be varied. So, for each setting, the resistance of each resistor is precisely known. And with switches S1 and S2 closed, these resistors are varied until the current in the galvanometer is zero. The bridge is then said to be balanced. So our question number 2, letter A, show or prove that under this balanced condition, the unknown resistance, all right, capital X, is given by the formula X equals uh, resistance M times resistance P divided by resistance N. And question letter B, if the galvanometer shows zero deflection when resistance M is equal to 850.0 ohm, uh, resistance N equals 15.00 ohms, and resistance P is equal to 33.48 ohms, what is the unknown resistance, capital X? We indicate and label each current that passes through each resistor as shown. And under the balance condition of the Wheatstone bridge, we can see that the voltage across resistance P is equal to the current I sub 1 times the resistance P, while the voltage across resistance N is equal to the current I sub 2 times the resistance N, because path uh, ABD is parallel to path ACD. So we say their voltages must be equal. That's why we are able to say that I sub 1 times the resistance P is equal to I sub 2 times the resistance N. And we denote this as our equation number 1. All right? Since resistance P and resistance X, okay, are uh, in series, all right, without current passing through the galvanometer, that is. So resistance P and the unknown resistance X are in series. We say that I sub 1 is also equal to I sub 3. And each of these currents is equal to, all right, the EMF, all right, in the battery divided by the sum of resistances P and X, all right? Similarly, I sub 2 is just equal to I sub 4 when there is no current through the galvanometer, all right? Because they are also in series. So I sub 2 and I sub 4, each of them is equal to the EMF of the battery divided by the sum of resistances N and M. So if we substitute the current I sub 1 and I sub 2 into our equation denoted by equation number 1, we get, all right, this, all right, the product of resistance P and the EMF divided by the sum of resistances P and X will just be equal to the product of the resistance N and the EMF divided by the sum of resistances N and M. All right? And canceling the EMF epsilon, right? We will get this simplified equation. Resistance P over the sum of resistance P plus X is just equal to resistance N over the sum of resistances N and M. And in just a little while, we will be able to determine the required working formula for finding resistance X. Multiplying the terms in our previous equation, we get this. Resistance P times the sum of resistances N and M is just equal to resistance N times the sum of resistances P and X. And then we multiply resistance P to each of the term inside the parentheses. All right? In the same manner, we multiply resistance N by the quantities inside the parentheses. So we get this. All right? The product of resistances P and N plus the product of the resistances M and P is just equal to the product of the resistances P and N plus the product of the resistances N and X. And canceling or eliminating uh, P times N, we will arrive at this working formula for the unknown resistance X. So that is, X is just equal to the product of resistance M and resistance P divided by resistance N. So that is our answer to question letter A. And moving on to question letter B, right? We can now determine the value of resistance X using this formula, right? That is 850.0 ohms. That's the value of resistance M multiplied by the value of resistance P, 33.48 ohms. And their product is to be divided by the value of resistance N, 15.00 ohms. Doing our math, we will get the value of the unknown resistance X equal to 1,897 ohms. And that concludes our tutorial for this topic. Till the next episode, mabuhay, Masya Allah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.